All right, folks. Welcome to this video again. It's been some time since I made another video. So this is again a series of videos that I'm going to be publishing through my channel that has been in high demand. There are a lot of you that has been asking for some deeper knowledge, some deeper clarification of how we can model PMSMs using MATLAB and Simulink, and then how we can implement FOC control. A lot of you might be doing this for your class projects, for research projects. So I wanted to create some content that will help you understand these different approaches. Now, keep in mind, I might not be covering all of the approaches, but with time, I'll be adding more and more content. So please feel free to let me know what you would like to see in the future. Now, again, there's another quite a bit of a lengthy set of videos under motor control videos, so feel free to check them out. This series is going to focus on how we can use MATLAB and Simulink to model the PMSM, and then moving on to FOC control. Okay, first of all, these are going to be shorter videos so that you can follow through, and I'll try to post them on a timely fashion as soon as I get a chance here. Okay, so now looking at these different modelings or models that you come across, basically you are trying to model an electromechanical energy conversion system, which is basically represented by differential equations in MATLAB. Okay, so you typically see what's called the rotor reference frame model, and then you'll also see stator reference frame model. Each of them have different purposes. They are used in different approaches depending on how much detail you need to see. But they pretty much give you very close results when you look at the outputs of these models. There might be some deviations, but relatively you get very close results. So if you are doing this for a class project, you can use either option. Now you also see that each of these, despite there are two reference frames, they also have a steady state model and a dynamic model. Each of them have these two different models. So in the steady state model, we typically assume that you have an algebraic equation, a linear or nonlinear, you have an equation which is not a differential equation. Meaning in the dynamic case, we try to capture the dynamics in that model. So you have a differential equation. Okay, so when you go into model, in order to model these, you can use differential equations and implement them in MATLAB, and I'll show you how to do that. Alternatively, you can use InPower toolbox. Now this toolbox that's provided by MATLAB has a lot of features. You can actually go into even implementing inverter and actual inverter. It does take some time for the model to run, but it's a good representation of what you see in a practical system to a certain extent. And if you but you do have to pay extra for the SimPower blocks if your school doesn't provide it. Now if you don't have that, don't worry, you can still use differential equations to model your motor. Okay, to model your motor. Now moving on to the PMSM models, you will see that you come across two different classes of PMSMs, permanent magnet synchronous machines. One is a surface mount magnet PMSM, and the other one is IPM, or interior permanent magnet synchronous machine. Now I have discussed these in my previous videos, so please feel free to go and check those out. In the models that we are going to discuss, you will be able to implement either of these types, because it's a matter of your direct and quadrature axis inductance. So if you choose to have the same inductance for the direct and the quadrature axis, you're going to end up with SM PMSM. But if you have different inductance, then you're going to have an IPM, and then accordingly you will have to modify your torque equation. So keep that in mind. Now when you look at the control variable, okay, so that adds model complexity. So for example, if you are implementing a PMSM with FOC control that performs torque control compared to speed or position control, okay, the torque control model is going to be much more simpler. Okay, your speed and position controller and the rest of the dynamic system will add more complexity. So my initial goal is to explain to you how torque control can be achieved. This can be easily explained as well as easily simulated, and this is a good step to get you started. Now, field oriented control, I have discussed this in detail. Okay, and in order for you to perform field oriented control, if you recall, you need your rotor position. Okay, now there are different strategies that are used in applications, that you use sensorless algorithms or censored algorithms, but here we are focusing on using a sensed or censored FOC for torque control, and for that we need rotor position information, right? Now you'll see that depending on the model you choose, you may or may not need to know rotor position information, but it is good to go into this discussion knowing how you can generate this rotor position information, because if you need it, for example, if you need to look at the ABC currents, you can directly, or you can use this approach that I discussed to get to that point. Okay, so this first video we're going to focus on how do we get this rotor position signal established. Okay, this is a key piece of information. Now, looking at, if you the other reason that you want to know your rotor position information is that when you look at your stator reference frame signals, you're going to need to know your back EMF, right? So your back EMF, if you recall, is going to be sinusoidal or trapezoidal depending on the type of the motor, and in our models it's going to be sinusoidal unless you force it to be a trapezoidal intentionally, and your back EMF is going to be a function of rotor position. So therefore you need this rotor position information. So that's another point of motivation for us to know how to generate rotor position. Okay, and going into the torque control application, keep in mind in a torque control application, the Pmsm, that is the driving motor, right, is only regulating torque. It's only controlling torque. It is not trying to manipulate or regulate the speed of that mechanical system. The speed is established based on the interaction between the applied torque and the load torque and the mechanical dynamics of the system. Okay, so if you think about a dynamometer where it's a controlled environment, in a dynamometer you'll have your PMSM, which is regulating torque, right? And then you'll have a dynamometer that's coupled to this PMSM, maybe a DC or an AC motor, that's regulating speed, meaning when there's a certain amount of electromagnetic torque or that's applied by the PMSM, the dynamometer is going to counter that torque so that it can maintain the speed of the shaft at a fixed value that you command it to be. Okay, so that's where the ease of implementation comes in terms of simulation, because you have two ways of establishing this characteristic of speed regulation. Okay, and I'm going to discuss these two briefly in a little bit, and I'll show you how to establish this regulation of speed concept. Okay, all right. So now going into these two, you can either assume that your speed is being regulated from an ideal dynamometer, very high dynamic system, or you can implement your dynamometer system with a mechanical equation, and then the DC motor model or AC motor model that's doing a speed regulation. Okay, again, this comes down to how much details you want to get into in terms of the simulation, and then how much processing time you can handle. For example, if you go into another model that is closed loop controlled, it's going to add more complexity to your model. Okay, so be aware of that. And instead, what I'll show you is an easier way to get around this problem by assuming that you have an ideal dynamometer that regulates speed without any transients. Okay, this is going to help quite a bit in terms of your modeling. Okay, so how do we do that? So here are the two approaches, and I'll show the models for these two. Okay, so the first case is that we assume the dynamometer is regulating the speed at a fixed value, and you can change this, by the way, with a variable. And that speed, this is the mechanical speed that gets integrated, which gives you mechanical position. And that mechanical position multiplied by the number of poles gives you electrical position. And with this remainder block, you can now convert this signal to a signal that looks like an electrical position signal. Okay, so in this scenario, you don't experience the mechanical dynamics. You're basically forcing the speed to be constant without having to handle the dynamics of the mechanical system or the dyno. Okay, so that's very easy, and I'll show you how to implement this. The second approach is, and this is where it gets complex, you need to implement, apart from your PMSM model that is performing field-oriented control for torque control, you're going to need to implement a DC motor model. This is your mechanical system, right? You have your inertia, your damping, your friction torque, and then you'll need to implement a DC motor model where speed is being regulated, and this system will have its own transients dynamics itself. Okay, so you have two electromechanical systems and one mechanical dynamics in this system. So this is a higher order system overall, making your model take longer time to run, and then it makes your implementation a little bit more complex. Okay, so these are the two different approaches, and I'll show you what this looked like, and then I'll show you an example of how to implement this position signal calculation. Okay, so let us look at this dynamic model implementation, and because we're not going to go into a lot of detail here. Okay, so you can see here, here is my PMSM model, and this is what I'm going to talk about in this series of videos. How do we implement this motor model? And then you can see there are three-phase currents, because this is a torque control application. We are regulating current through field-oriented control. Okay, and you can see these ABC currents being fed back to this rotor reference frame transformation block. Okay, and then they are regulated using the PI loop, and then you are applying the voltages back to the motor using an inverter, or supposedly that something that looks like an inverter. Okay, so this represents the PMSM. Okay, and on the right hand side you can see here the DC motor, which is acting as a speed regulator, and it has all the mechanical dynamics, your inertia, your damping and all that, along with the DC motor controller. and here we have the position signal calculation based on that dynamic response of the mechanical model. Okay, so this is one approach, a complex model that you can implement, but a possible solution. You can still use this. It does take some time. And then the second option is this one. So if you are getting started with PMSM modeling, I recommend you trying this one. Okay, if you want to generate your position signal. So here you can see that we establish our speed uh, as a variable, so you can actually make this a step response or any waveform that you want, because this is just a constant block. Okay, this is just a constant block. Instead of a constant block, you can replace it with a function, and then we integrate that to get to position, and we convert that mechanical position to electrical position here, and then we use a remainder block to wrap it around to create the triangular waveform. Okay, so before I run this simulation, I'll show you the model settings that I'm using here. For some of you it might be useful. I typically use fixed step ODE4 with 1E minus 4 as a step size. This has typically worked out overall in my model. So if any of you are looking to do something like this, you can start with this, and of course you can switch to something different if you prefer. Now if you run this, let's see what we are going to see, right? So you'll see that here, there we go, right? So oops, I think I might want to shrink this here. There you go. So you can see here you have your electrical position once wrapped around 2 pi versus without wrapping around 2 pi, right? If you zoom in, you can see that practically speaking, if you look at a position signal on a dynamometer or an actual motor drive system, you're going to see something like this. But again, this is electrical position, right? Your mechanical position may span over number of pole pairs or number of electrical cycles, so keep that in mind. Okay, so you can see that you have a position signal that is continuously increasing at a constant speed, and then since we are wrapping this around 2 pi, you see this triangle or sawtooth kind of a waveform which represents an actual position signal. Okay, so folks, this is about how we can generate position signal for our models, which are going to be coming up in future videos, and I'll explain these different types of models that you're going to be implementing and how we can use this position information to our benefit. Okay, so again, thank you for watching, and please feel free to let me know if you have any questions on this material. Thank you.